Hi, welcome back. This is going to be the 7th lecture on topology and second lecture on continuous function between topological spaces. So hope that I will be able to complete this section today. I'm not very sure because there are quite a few things which usually textbooks avoid, but I would like to do that. But let's see. Yeah, this is going to be my new digital notebook designed by one of my students, or whatever you call it. Yeah, so let us go ahead. Yeah, so let us recall, yesterday we found something very interesting. Do you remember that? This is a review of yesterday's thing. On R with a lower limit topology, I looked at the set A, which is close to 0, 1, or more generally of this kind. Okay, and we will define the so-called indicator function, okay, which at x equal to 1 if x is in A, 0 if x is not in A. Okay, and we proved this is continuous on R with the lower limit topology, and we also observed it's not continuous on R with the usual topology. Alright, okay, but if you really go through the proof, you would have found something very interesting, and that's what I wanted to check. Okay, let me see. I want it to be continuous. Yeah, right. Okay, so where is the next one? Yeah, oh. All of a sudden I seem to get some problem. Okay, I do not know, but anyway, let us go through that. Yeah, so if you go through the proof, well, I can ask a more general question. Suppose x is tau is a topological space. Okay, and let us assume that A is a non-empty subset of X. Okay, then I define F to be the indicator function of A. I hope all of you understand this. Okay, now suppose F is continuous. Assume F is continuous on X tau. What can I conclude? Okay, if you go through the proof, there is something which is very interesting, which all of you should have found out. That's our aim. So let us see whether all of you get that. So what does it mean? Like yesterday, we have 0, I have 1. So let me just take this kind of open interval which are distinct. Alright, and so if V is an open set in tau u, this is R, right? R tau u, right? And we what are the possibilities? If 0 is in V and 1 is not in V, then we found out F inverse of V is what? X minus A, X difference A, which is A complement. And we also found out if 1 is in V and 0 is not in V, then F inverse of V is A, right? And what is our V? V is either an open set, therefore this has to be open, and this also open. Do you follow that? Therefore if F is continuous, that is indicator function of A is continuous, implies A and A complement are open. This is what we observed in the earlier case. Yeah, right. The next one, okay, converse. Is the converse true? That's also true, because if both are open, then let's look at that. Okay, if assume that A and A, this is given, this is hypothesis, A and A complement are open, right? Then F inverse of V, depending upon 0 belong to V, 1 does not belong to that, that's going to be a complement. 0 is in V, 1 is not in V, and so on. Yeah, therefore this is given to be open, right? And if 1 belong to V and 0 is not V, then F inverse of V is A, and this is also given to be open. And suppose both belong to V, right? In that case, F inverse of V is going to be all of X, right? And what is the left out case? Suppose 0, 1, none of them is in here, V, then F inverse of V will be empty set, that's also open. So what I have shown is for every V open in tau u, F inverse of V is open. That means F is continuous. So what do you think I have proved? I have proved the following result. Okay, this is what we have proved. The following result. Okay, let A, assume this is non-empty, be a subset of X, then I indicator A is continuous on X tau if and only if A and A complement both are in open the topology. Okay, pause, review, proceed. Okay. Now let's look at another example. I forgot the number game. Anyway, maybe something like 8th, 10th, something, right? Okay. Now suppose here, F from R of U to R is again is continuous. See, now do you see that I am restricting myself to real valued continuous functions? Okay, right. And assume that F of R, that is the image, is contained in plus or minus 1. That is, it takes only either 0 or 1. Or it can even say it takes only value 0 or 1. Right? Then what do you find? By going through the last, okay, arguing as earlier, right? Let me take 0 and 1, this kind of intervals. This is my V, right? Suppose V contains 0 and V does not contain 1, then F inverse of V, okay, call it U0. Okay, this is open. U0 is open in tau u. And similarly, let us call U1 to be F inverse of V, where V is like this, contains 1 but not 0. Then what do I know? This again and tau u, right? Do you find something very interesting? Now notice that my R is U0 and U1, and this is a disjoint union. Because F takes only two values, 0 or 1. You understand? Therefore, given any x, then f of x is 0. In that case, it's going to be in u0. Or if f of x is going to be 1, in that case, it is 1. Do you follow that? X in R, fx equal to 0 implies x is in u0. And similarly, fx equal to 1 implies x is in u1. Right? And they are disjoint because if there is a common thing, then fx is as 0 as well as 1. That's a contradiction because f is a function. Therefore, this is a disjoint union. Okay? Make sure that you understand this. And we also found out something very interesting. What did we find out? We found out that u0 is open and v0, u1 is also open. And u1 is u0 complement. And u0 is u1 complement. Do you understand? Right? And u0 is not empty, u1 is not empty. If, okay, assuming f takes both the values 0 and 1. Okay? If, this is if f of r equal to 0, 1, then this happens. Do you follow that? Because there is an x such that fx must be 0. And there is another y such that f of y equal to 1. Therefore, u0 is not empty, u1 is not empty. and so let me call it u. Okay, you follow that? Let me stick to u naught. Okay, and u1 is u naught complement. Both are open and both are non-empty. Okay, now I'm going to say this cannot happen. I'm going to say this cannot happen. Okay, let us assume without loss of generality. Okay, okay, let us say 0 belong to u0. That is f of 0 is 0. Yes, you follow that? Yeah. Now since u0 is in tau of u, that means there is epsilon positive, so that minus epsilon to plus epsilon is contained in u0. Right? What I plan to show is u0 is all of R, and hence u1 must be empty. Right? But this is a contradiction. Why? Because I assume, are you following? This contradiction shows f cannot take both the values 0 and 1. Because how did I arrive at the contradiction? If f takes both the values 0 and 1, then u0 is not empty, u1 is not empty, and u1 is u0 complement. Right? Now I am going to prove, assume 0 belong to u0, okay, or any, for that matter, any x. Then I will take x minus epsilon to x plus epsilon. Okay, for convenience sake I am assuming 0. Right? I am going to show u0 is all of R. If that be the case, what can I conclude about u1? Then u1 must be empty. Okay, this contradiction shows f of R cannot be both, f cannot take both the values 0 and 1. F of R cannot be the two elements at 0, 1. Since I already assume 0 belong to u0, that means f of R has only one element, namely 0. That is, f is a constant. Do you get what I am saying? Please, okay, pause, review, proceed. So this would imply f is a constant, and since f of 0 is 0, then f is identically 0. If it is 1, it will be 1. Do you follow that? So what have I shown? If the result is true, I would have shown that, okay, if f from R tau u to 0, 1 is continuous, so this is R, and f of R is contained in 0, 1, that implies f of R is equal to a singleton, either 0 or 1, one of them. That's it. That is, it must be a constant. Do you follow that? I just want to teach you topology. I don't want to go through the textbook way. Okay, theorem proof. This kind of thing will make you comfortable with the working knowledge about topology, open sets, etc. That's what I want. Okay, let us go through the proof. So what do I want to do? I want to prove u0 is R. So I already know u0 contains minus epsilon to plus epsilon, right? So I am going to say 0 belong to this, right? So I want to show the entire 0 infinity or minus epsilon to infinity is contained in u0. Okay, this is what we want to show. Yeah. So how will I do that? If those of you have seen my analysis, etc., you will know the trick. So let us construct the set E to be set of real numbers A in R, so that minus epsilon to A is contained in u0. That is, look for the interval like this. This is my A. Minus epsilon to A is contained in u0. So this is non-empty. Why this is non-empty? Epsilon belong to this, right? Okay. Now what are the possibilities? So this is a non-empty subset of R. Therefore either it is bounded above or not bounded above. Okay, I am going to show it's not bounded above. That's it. Okay. So suppose it's bounded above. Okay, suppose this is the first case, and second case not bounded above. Suppose E is bounded above. Okay, what does that mean? Okay, this is a non-empty set bounded above. Therefore, if you remember in real analysis, there exists alpha, a real number, so that alpha equal to the LUB of E. If you are fond of the word supremum, supremum of E. Yeah? Is that clear? Now, where does alpha belong to? Alpha is an R, and remember my R is U0 union U1. Right? This is U0 complement. Right? Okay. Now, therefore, either alpha is in U0 or alpha is in U0 complement. One of these two things should happen. Yeah? So, think of R like this, and this is my U0, this is my U0 complement, therefore my alpha either is here or here. Yeah? Right. Suppose alpha is in U0. Now what do I know about U0? It's open set, and alpha is an element of U0. Therefore what do I know? There exists a delta positive, so that alpha minus delta to alpha plus delta is contained in U0. You see that? You cannot, there is no escape from analysis. Okay? Right. Is that alright? Now I have alpha. This is the LUB of E, and you have alpha minus delta. Therefore, this is not an upper bound for the set E. Since it's not an upper bound for the set E, I know there exists an A in E, so that, okay? Therefore, there exists alpha minus delta, not an upper bound. That means there exists A in E. So that what happens? Alpha minus delta should be less than A, less than or equal to alpha. Because alpha is least upper bound, in particular an upper bound. Okay? Do you follow that? Now what do I know about A? Yeah? Oh, sorry, I don't need this. I take back my word. I don't need this. Right? This is contained in this. Right? Yeah, no, I'm sorry, please allow me to think. Okay, let us assume, okay, alpha minus delta not an upper bound of E, imply there exists A in E, so that alpha minus delta less than A, less than alpha. Since alpha is in E, A is in E, that means minus epsilon to A is contained in U0, right? Now let's look at that. So I have alpha minus delta, this is my A, right? This is alpha plus delta, and this object is contained in U0, and I know up to this is contained in U0. Therefore, what is the union? Okay, are you following? Therefore, minus epsilon to A union alpha minus delta to alpha plus delta equal to minus epsilon to alpha plus delta. This is contained in U0. Do you accept it? Maybe I should use a different thing. Okay, this is minus epsilon to A, and this is minus alpha to alpha plus delta. This is also contained in U0. You understand? Therefore, that union must be contained. But the union is nothing other than the interval minus epsilon to alpha plus delta. So what do I get? By our definition of E, alpha plus delta, this implies alpha plus delta is in E. But what was my assumption? Alpha is the LUB of E. Therefore, alpha plus delta should be less than or equal to alpha, but alpha plus delta is strictly greater than alpha because delta is positive. So this contradiction shows this is a contradiction. So, right? Therefore, what can I conclude? I conclude alpha is not in U0. You follow that? Therefore, where should alpha? Since alpha is an R and R is U0 intersection U0 complement, therefore alpha must be in U0 complement. Right? Go back to the thing. Yeah. So now alpha is somewhere here in U0 complement. Let us see why it's a problem. Now therefore now alpha is in u naught complement. What do I know about u naught complement? This is open. Therefore there is an r positive, so that alpha minus r to alpha plus r is contained in u naught complement. Do you follow that? Yes. Now let's again use the same trick. See how many times I'm using reanalysis. Okay, that alpha is the least upper bound. That's why please learn least upper bound, greatest lower bound, etc. Okay, go back to my videos on upper bounds, lower bounds, LUB, GLB. Learn them well. There is no escape. Now alpha minus r is strictly less than alpha. Therefore alpha minus r not an upper bound of what? E. Therefore there exists, let us say, a B in E, so that what happens? This is alpha minus r, this is my B, this is alpha plus r. And where do all these things contain? This is contained in u naught complement. Yeah, do you follow that? Yes. And what is the relation? So alpha minus r is strictly less than B, less than or equal to alpha, less than alpha plus r. How many of you see a contradiction? Since B belongs to E, what do I know? Minus epsilon to B is a subset of u naught. Right? You follow that? Yes or no? Therefore, in particular, if I take C a point so that alpha minus r less than C less than B, for example, it could be midpoint of alpha minus r and B. Okay? Right? The C has to be in u naught. Yeah? You follow that? Right. So of course I am assuming that alpha r is small enough, etc. Right? Okay. Right. Now why is this a contradiction? But remember, C belongs to the interval alpha minus r to alpha plus r, which is contained in u naught complement. Because where does C lie? C lies between alpha minus r and B. But where does the whole thing lie? All these fellows lie in the interval alpha minus r to alpha plus r. But that's in u naught complement. But C is in u naught. C is in u naught complement. Therefore, what is the conclusion? Hence, okay. So this is the contradiction, right? Therefore, C belongs to u naught as well as u naught complement, a contradiction. So pause, review, proceed. If you are not very conversant with the least upper bound, etc., you'll have problem. Okay, that's why I keep saying learn those things thoroughly. Okay. Now, why does this contradiction? Therefore, if alpha, which is LUB of V, I am assuming is bounded above, and therefore LU alpha. Therefore, alpha must be in R. Therefore, it must be either in u naught or in u naught complement, and exactly one of them. I said, if it is in u naught also, there is a contradiction. If it is u naught complement also, there is a contradiction. Right? So, what do I conclude then? Therefore, I conclude he is not bounded above. Do you accept it? Yeah? Right? What was E? E was set of what did I say? A in R, so that minus epsilon to A is contained in u naught. Okay, this is not bounded above in R. And from this, I am going to say this implies, okay, my u naught is all of R. U naught is at least u naught contains minus epsilon to infinity. Okay, I am going to prove that. Why? Okay, start with the NAX, okay, in the interval minus epsilon to infinity. Right? I have to prove X is in u naught. right? This set is contained in U0. You understand? Now what do I know about X? The set is not bounded above and X is a real number, therefore X is not an upper bound of E. If it's not an upper bound of E, what does it mean? That means there exists A in E such that X is less than A. Right? Remember, my X is already in minus epsilon. This is already granted. X is in the interval minus epsilon to infinity, therefore X will be greater than minus epsilon. Do you understand? Do you understand that? Okay. Now do you see a problem? Since A is, this implies minus epsilon to A is contained in U0, because that's the way we define E. Right? But X belongs to minus epsilon to A. Therefore, X belongs to U0. You understood that? Therefore, what I have concluded? I have concluded the interval minus epsilon to infinity is contained in U0. Okay, so I have minus in epsilon and all these things is contained in U0. Now what is that I have to prove? I wanted to prove U0 is all of R. That means I have to prove minus infinity, okay, to infinity equal to R. Right? Entire R. Okay, this is a very stupid way of writing, but anyway. How do you think I should prove? Okay, I am going to leave it as an exercise. So what did I do? Here I went to the right side, then I argued with bounded above, right? So what do you think I will argue? So you construct a new set E such that it is set of B in R such that B to epsilon is contained in U0. Therefore minus epsilon is here. Right? Now argue whether it is bounded below or bounded up, not bounded below. Okay? And bounded below will lead to some contradiction. Therefore it's not bounded above. If it's not, it's not bounded below. If it's not bounded below, then you have to prove minus infinity epsilon is contained in U0. And you already know minus epsilon to infinity is contained in U0. All these things will prove U0 equal to R. Okay, don't get disheartened. Please think of this as an opportunity for you to learn LUB GLB properly. Because I know most topology teachers avoid analysis, difficult analysis. Okay, they just want to work with only set theory, but nothing to the real numbers, etc., where you have to learn some analysis. Please use this as opportunity. Okay, so don't give up. So use this as an opportunity. And complete the proof. Okay. So finally, what do you think I have proved? It's a bit of thing. So what I have proved is, in fact, I would have liked to prove this when I discuss about topology, usual topology on R. Okay, but I just wanted to give a so what we did was, if f is a continuous function from the usual topology and assume and f of R, okay, is contained in 0, 1, then we wanted to say f is a constant. Right? If not, what did we find? If I take open intervals like this, 0 and 1, then I found f inverse of v is 0, f inverse of v is u0, f inverse of v is u1, etc. Right? Then we proved both are non-empty. If this is equal to this, then u0 is open and it's non-empty, u1 is not open, non-empty, and they are disjoint, and this one. Okay, you follow that? Now what I proved that, therefore go through this. What I actually proved is the following result. let U be a subset of R, be a non-empty open set. Assume that U, okay, complement is also open. Then U is all of R. Yeah, how did I prove that? Assume, let's assume that with the loss of generality U0 belong to S, then I have minus epsilon to plus epsilon is contained in U. Then we wanted to say this is contained in U, and similarly minus infinity epsilon is contained in U. Okay, that's a proof we gave. Okay, are you confused? Okay, go back and understand. It's always good to discuss with your friends. Okay, this I could have proved in the first 4 or 5 lectures on topology. Okay, these all be used. Yeah, so assume how did I prove? The proof is given above. Yeah, okay. Okay, so I think it took more time than expected. Alright. See, remember I said I will explain almost all concepts using our examples. Alright. So we had used discrete, indiscrete, VIP, countable, co-countable, outcast, everything. But still, there are 2 important class examples which are very important. One is metric space context. The other one is something with R and Rn. We have done already with Rn, but I want to do. Okay. Right. So let me do a metric space concept. Suppose I have 2 metric spaces X and Y D, and remember I do not write dx and dy. Okay. Suppose f is a function. I want to know when f is continuous at A. And what is the topology? Since if I have a metric, I have the metric topology here. Okay, tau x, and I have the metric topology tau y here. Do you understand? So the continuity is with respect to these 2 topologies. Are you following? But I want to formulate the definition of continuity at a point A using the metric. Okay, so what do you want to do? You want to formulate an equivalent definition. Using the metric D's. So when I say f is continuous at x, what does it mean? If f as a map from x tau x to y tau y is continuous at A. And what is tau x? This is a metric topology. This is a metric topology. Are you following? So let us do that. Okay. So this is my metric space Y. This is my metric space X. So I have a point A. Then what do I know? I have a point FA. So what do I have? I have F, which takes here. And so since F is continuous at A, what do I know? You give me any open set around FA, then I can find an open set containing A, so that F maps the open set containing A to this open set which contains FA. Right? Yeah, let V be any open set containing FA. I can find an open set U containing A, so that F of U is contained in B. I'm sure all of you remember that, right? We have been using it. Now again, let's go back to my trade secret which I said. What is the simplest open set which contains FA? They are open balls, right? So I can take an open ball, okay, V to be an open ball centered at FA, and usually I can take R, but as all of you know, continuity uses epsilon delta, I'll choose epsilon, okay, where epsilon is positive. You follow that? So I have an open ball around this. This is my V, FA, epsilon, right? Yeah. Now since F is continuous, now what do I know? I know that this is open. any open ball is open, therefore this is open in tau y. That is with respect to the D metric on y. Since f is continuous, what do I know? I know that there exists an open set U. Okay, therefore there exists U open where? In the metric topology on X. Okay, so that A belongs to U and f of U is contained in V, which is V f a epsilon. Yeah, right. Now A belongs to U and U is open in the metric topology. Therefore, what does it mean? Okay, therefore there is, go back, this is my U, therefore it says that there exists a ball B A delta, right? Are you following? Therefore, since A belongs to U and U is in tau of X, there exists a delta positive so that B A delta is contained in U. Right? So what do you think I have proved? Now take any X in this open ball B A delta, it is already in U. Therefore Fx is in B. That means the distance between Fx and Fa is less than epsilon. Do you understand that? Yeah? Start with any x in B A delta, that is same as saying take any x so that distance between x and A is less than delta. Then since the ball B A delta is contained in U and F maps U into V, F of x must lie in B. But V is the open ball B A epsilon. Therefore distance between Fa and Fx must be less than epsilon. Do you understand? Therefore we have concluded, given epsilon positive, see I took any epsilon, right? What did I find? Then there is a delta positive. So that what happened? For every x in X, such that distance between x and A less than delta implies distance between Fx and Fa is less than epsilon. That is, if x belongs to B A delta, implies Fx belongs to B Fa epsilon. So you see that this is the usual definition, epsilon delta definition of continuity for metric spaces. This is nothing else than epsilon delta definition of continuity of F between metric spaces. Is something similar to R, right? The same way. Do you follow that? So what do you think I have proved? I have proved that if F from xd to yd is continuous at A, okay, then if this is the hypothesis, then for every epsilon positive there is a delta positive, so that x belongs to B A delta implies Fx belongs to B Fa epsilon. So right, that means our topological definition of continuity at A implies metric definition or epsilon delta definition of continuity at A. So what is the next question I should ask? Whether the converse is true, right? So assume that F from xd to yd. Now just go back, I use the same d. Now you can see that, see when I write distance between Fx and Fa is less than epsilon, should I write y? Because I always think I am intelligent and my students are intelligent, my viewers are also intelligent, because Fx and Fa, where do they live? They live in y. I am looking at their distance. So I should be naturally using the metric or the distance function on y. And similarly x and a, where do they live? They live in x. So I don't have to write x. You see that? So always depend upon native intelligence of people rather than assume that they are stupid. Okay? Right, anyway, come back. So let us assume this is continuous at a, according to epsilon delta definition. Right? Then I want to know whether it is continuous according to that thing. Okay? Topological continuity I have to establish. The proof is easy. I should actually skip because I could have referred you to the earlier case. So this is my y and this is my FA, and start with any open set V. Then what do I know? Okay, there exists an epsilon positive so that BFA epsilon is contained in V, right? And this is my x, this is my a, right? Now I have an epsilon given and my function f is continuous according to epsilon delta definition. Therefore what do I know? There exists delta thing, BA delta, right? So that for each x here, okay, this is my BA delta. Therefore my fx should lie here, right? So what do you think of, but what do I know about BA delta? This is an open ball in X, therefore this is U, this is an open set, right? Therefore what I have found, you gave me an open set V, I found an open set U, so that f of U is actually contained in B FA epsilon, but that's contained in B. Therefore I found this. Given any open set V containing FA, I found an open set U, namely BA delta, so that F maps this open set into this open ball and hence into the open set V. Therefore F is continuous at A. Okay, according to topological definition. Do you follow that? So I think this is good enough. Okay, pause, review and proceed. Okay, and in the next lecture we will talk about I still have some time. I'll just look at, see, do you remember we said R with a co-countable topology, and if I have a real valued continuous function, f is a constant. That is, I said in general topology spaces there may not exist non-constant real valued continuous functions. Yeah, I proved that by this example. But if I have a metric space, okay, there exists an abundant supply, a lot of this is something very interesting. Why? You fix a point A in X, right? Let us look at f of x equal to distance between x and A, right? You see that distance is already a function of two variables, x cross x, to real valued function of two variables. So what do I do is you freeze one of the variables, second variable you freeze it, and therefore it becomes a function of one variable. Therefore I have a very natural real valued function on any metric space. Do you understand that? That's something very interesting. Yeah, because D itself is a real valued function of x cross x. Therefore if I freeze one of the variables, I get a real valued function on x. The only thing is I have to check whether it's continuous or not, right? First notice that what is f of a? It is 0. And suppose x is not equal to a, what is f of x? It is not 0. That's it, right? In some sense there is a function f whose value at a is 0, whose value at x is not 0 if a and x are different. So that is what we mean by it separates points. Now is it continuous? So let us look at the definition of thing. What is that I want to prove? I want to prove f is continuous at A. Now I can use epsilon delta definition. Yeah, right. So I have FA. Let me give FA minus epsilon, FA plus epsilon. Then what do I have to do? This is my A. I have to find a delta ball around this, right? Yes or no? So what is that I want? Yes? Yeah? So let us look at what is fx minus fa, right? I want to estimate this. To check continuity, I have to estimate this. This fellow is nothing other than distance between x and a and distance between a and a. You see that I want to find a delta so that for all x here, fx should lie in this interval is same as saying I want to say this is less than epsilon. Yeah, but fa is 0. That means I have to check distance between x and a is less than epsilon. Right? What does it mean? This means, what does it say about x? Are you following? This is 0. Therefore, mod fx must be less than epsilon. But fx is already non-negative. That is dxa. So the condition is, if x belongs to be a delta, I want fx mod fx minus fa should be less than epsilon. That is same as saying distance between x and a should be less than epsilon. So what is your choice? Take delta equal to epsilon. So if I look at be a epsilon, if x belong to that, then what is fx minus fa? That is, this is distance between x and a minus distance between a and a. But that is the distance between x and a because non-negative, but that's less than epsilon. So I proved it. You follow that? Yeah? Please pause, review, proceed. So, in the general topological space, there may not exist non-constant real valued continuous functions. But on a metric space, we have a lot of real valued continuous functions. For example, let us look at this. This function is continuous. We proved it. It's not constant because f of a is 0, whereas f of x is non-zero. If x is different from a, for any x different from a, you follow that? Okay. I hope you understood all these things. Please review. Usually in topology, lots of such exams are not given. People are immediately go to, as I said, theoretical results. But when you want to get the grip of the subject, you have to learn. You see that we have to intimately work with the topology, what kind of open sets I should look for. This is what makes topology interesting. I hope you enjoyed. I will stop it. We'll meet again.